Hello. For my presentation, my topic is the rise of the system on chip and how it changed the way CPUs are designed. So, this connects directly to what we studied in class, which is the von Neumann model, the CPU components, the buses, the memory architecture, and it shows the modern evolution of computer architecture. So, before smartphones, computers followed the classical model, which is the classical CPU architecture, which means CPU on one chip, the RAM on separate modules, GPU on another, and they were all connected using an external buses. So this follows the von Neumann model, which is one path between the memory and the CPU via the data bus. But this, of course, raises a problem that we all know, which can be summarized into three words, which are distance, delay, and power. So as CPUs became faster, the distance became the bottleneck. And of course, the smartphones made the problem even worse. They needed good performance, a long battery life, low heat, and a smaller size. So engineers asked one simple question: why keep everything far apart? Why not put them all onto one single chip? And this is where the SoC came, which is the system on chips. So a system on chip is simply this: all the major components of a computer combined on a single piece of silicon. So as we can see here, uh, we have the CPU core, the GPU, the memory controller, the cache hierarchy, the neural engine, the image processor, the security module, sometimes even the RAM or the unified RAM onto one single chip. So, as I said before, this is not a new architecture. It's the same von Neumann CPU, just much closer to everything it talks to. So why does this matter, and what are the architectural advantages of this new technology? Of course, it's speed, power, and size. So for the first thing we're going to talk about is the power efficiency. We have smaller distance equals less energy per bit. For the second advantage, we have the size. It fits easily inside our pockets. And for the third, we have the thermal control. Of course, we have lower heat because we have lower energy cost. And finally, the integration and speed. Of course, if we have less bus delay, then we have faster fetch, decode, execute cycle. And this improved the user experience. We got smoother apps, better battery, and higher processing power. And the good examples of that are the Apple A series and M series. For example, the modern system on chips like Apple's A17 Pro or Qualcomm Snapdragon, they pack 6 to 8 CPU cores, a very strong GPU, dedicated AI hardware, plus 16 neural cores, a RAM controller, a encryption engine, and an image signal processor, all into one single chip, which is very fascinating. And this is why phones today outperform many laptops from 8 to 10 years ago. So how smartphones drove this change? Smartphones forced this evolution because they needed high performance for the games, the AI, the camera, high efficiency for the battery, and of course a tiny space to fit inside our box, as I said earlier. And future laptops do use this system on chips, as I said before, like the Apple N series that already started moving towards this direction. And of course, this replaced the old philosophy, which is the separation of components. It became outdated, so now integration is the key to performance and functionality. And as I said before, a laptop can afford a big motherboard and cooling fans, but a phone cannot, so the system on chips was the only possible path. So again, the system on chips are the same architecture, just a smarter integration. So to summarize all of this, a system on chip is the same computer architecture that we learned, which is the CPU, the registers, the buses, the ALU, the memory, but integrated tightly to reduce distance, latency, and power. And smartphones for this innovation. And that leaves us with a simple question: does the von Neumann bottleneck still matter if everything is much closer? Because this somehow solves the bottleneck not logically, but physically. Thank you so much for your attention.